reinforcement learning for the metaverse.
Hello everyone. I'm very honored to be here to give the presentation to you. So today I want to introduce the asynchronous and user-centric reinforcement for the recently futuristic notion, the metaverse. So specifically, I will talk about the asynchronous multiple processes in metaverse and the user-centric scenario. This interesting scenarios also brings new problems and also new solutions. The first one on XR 3D real-time reconstruction in the metaverse. So please first let me shortly introduce the background of the metaverse. The metaverse is an extension, complete solution, a simulation, and a mirror of the real world. So the extended reality, the XR, is a very important technology which empowers the metaverse, and it also forms the pillars supporting its applications. However, the XR is just an umbrella term for any alteration of the real world with digital elements. But there are many two kind of technologies, AR and VR. I think we're all very familiar with these two things. So AR provides the users with a view of the physical world with overlay of digital elements. While virtual reality, the VR is a fully immersive and digital world. But no matter VR or AR, they both improves the interactivity and the connectivity between people. So with the frequent demands of reflecting the real objects in the virtual world, we need to consider an instant replication of 2D physical world images into a 3D virtual world scenes. So the mobility of the XR devices are highly aware, like, especially for the VR devices such as the HTC Vive and the MetaQuest headset, because we need to wear it and walk around in the room and in the space. So the mobility of these devices are highly aware. So these devices will reduce their weight at the sacrifice of their local computation ability, and which leads to the insufficient local computing power. So we need to consider that we need to transfer the physical images from the real world to the server, and the server will do the integration and most of the computation tasks, and send the generated digital twin back to these users. So this is a very specific scenario. This is a real-time 3D reconstruction. And these two GIFs are taken from the new recon, which is done by Sun and their team, and was published in this VPR 2021. You can see from these two GIFs that their performances are astonishing. And this must be a highlight application in the metaverse. So for such a scenario, there arises some very interesting problems. Like in the uploading stage, the users will upload the real scenes to the server and to generate the 3D models. And in the downlink stage, the servers transfer the generated models to each user. So you can see that the data sizes in these two stages are highly asymmetric. So maybe like we separate this whole transmission to multiple terms. Like each term will have an uplink stage and a downlink stage. So the influences between the synchronous process cannot be neglected. Because in such circumstances, the rendered 3D virtual objects can possibly be orders of magnitude larger than the uploaded scenes. So the differences in these datasets introduce an issue of sensitivity. So where a slight change in the uplink stage may possibly induce a dramatic change in the downlink datasets. So this is very harmful to the reliability of the whole system. So to ensure the reliability, the multiple processes need to be considered in tandem. And to avoid the over delay in one downlink transmission, we need to set a time limit to each downlinker. So this is a very normal way to set in the wireless communication field. So, and if the downlink delay exceeds the time limit, we said this at this turn, this data is lost and need to retransmit in the future turns. So, in such a system, there are many things to optimize. For example, the most intuitive things is the device access and the computation resource allocation. So for the device access, this can be some like channel access and the device selection in the uplink stage. And in the downlink stage, we use the same device selection or channel access in the uplink stage, and we allocate the remote computation resources to all the users. So therefore, the downlink optimization is totally based on the uplink stage. And some measures in one term, such as the round delay and the average transmission rate of each user, can only be obtained after all the agents have done the actions. So the agent here points the reinforcement agent, which handles the two kinds of optimization tasks. So this is a multi-stage joint optimization problems. And these problems is quite hard to tackle with the traditional optimization strategies such as the convex optimization. Because first, the user's left to transmitted data is a continuous variable. Like the data of each user cannot be transmitted totally in just one term. So it's a multiple term thing. And this is a sequential, which causes the t variable, which means the time step variable in the problem formulation. So if we use the traditional optimization strategies, such as the convex optimization, the computation complexity can be daunting. And besides, the problems in the truly real-world scenario are really naturally non-convex. So relaxation is a good strategy, but it's not always suitable. Because it may lead to the solutions that are far from the original problem, and there are many constraints. Like we need to avoid the inseparable mixed integer linear programming and some other tough stuffs. So if we use the other iterative optimization strategies such as the bisection search and the outer approximation, this will also lead to a very huge computation complexity. So the model-free reinforcement learning can achieve near optimal solutions if we feed it sufficient training. And it can handle very complex joint optimization problems by the well-designed algorithms, structures, and the reinforcement environment. So before talking about the reinforcement learning, please first let me thoroughly introduce the background of the reinforcement learning, because I think that maybe some of our audience are not very familiar with this. So when we are embedding a reinforcement learning strategy to solve a problem, the first thing is to create a comprehensive environment to let the agent train and learn in it. So here I take the Super Mario as an example because I think this is a very easy and famous game. So if we want to train this Super Mario character to play better and better in this environment, we need to feed the agent a state, and the agent will take the best action under the state. And we give it a reward as a feedback to tell it that if this action is good or not. So in this scenario, like the game frame can be the state. And when the agent gets this state, it will choose the best action. The actions can be like moving left, moving right, jump, or idle for this frame. So it's basically the joypad control. And the reward is a self-defined thing. And the reward is very important for setting a reinforcement environment. In this scenario, like if the Mario dies, we can give a very huge negative penalty. While if it reaches the destination of this stage, such as the flag of this stage, we can give it a very high reward. So the objective of this agent is to maximize the accumulated rewards in an episode. So the episode starts from the game start and ends if the Mario died or it reached the destination. Let's back to our scenario. In our scenario, the things are quite more complicated. Because in the Super Mario scenario, it's just a single agent reinforcement learning, and they are just state for the single agent and the action for the single agent. Well, in the real-time theory reconstruction scenario, the states and the rewards actions of the two agents are totally different. Besides, like for the uplink action, the device access, like the device selection and the channel access, it's a discrete action. And in the downlink, the remote resource computation, resource allocation, this is a continuous variable. Like if we allocate the downlink transmit powers to each user, it must be continuous. So the discrete action and the continuous action will lead to totally different algorithms. So and then I will shortly introduce the mainstream of the basic algorithms of reinforcement learning. The widely used one is the deep Q learning network, which is all short for DQN. This is a very commonly used reinforcement learning algorithm, and it's simple but with remarkable performances under many scenarios. So in this, this first line is the update function of this DQN, but I won't derive the math in detail. I will just explain the inside of this algorithm. So assume that if we have the best policy, if we have the best neural network, we can select the best actions under every state. So the value of the current action should be equal to the reward plus cost by it plus the reward of the best actions in the following states. And in DQN, we only consider the TD1 error. So we only consider the current state and the next state. So the value of the current action should equal to the reward plus the value of the best action in the next state. So here, the Q is the action value, which is the value of action A under state S. And the alpha is the learning rate, and the gamma is the discount factor with time steps. Because the action in the the action far away from this current state will have less influences on this state. So you can see from this that DQN must predict the values of every action, and it directly selects the best action with the maximum Q value. So it is not feasible in continuous action space. So let's take a simple example. Like here, we have just two discrete actions, like action 0 and action 1. It's very easy to predict the values of these two actions, and we just select the action with the bigger value. Well, if the action is from 0 to 1, it's not possible to evaluate, to predict the value of every action, right? So to solve the continuous action space problem, people invented arithmetic structure, and this is a very well-known and state-of-art structure. So in this structure, we use two separate neural networks. The first is called actor, and the second is called critic. So for the actor, it will train a policy to select the action, and it is updated through the policy gradient. The policy gradient is very similar to the gradient ascent. So here you can see that the pi theta in this equation means the parameters of the actor neural network, and it will select the action AT under the state ST. The GT here is the cumulative reward caused by this in this whole episode. And thus we use a separate critical networks to evaluate the action selected by the actor. So why we say that these kind of strategies can solve the continuous action problem is because that in this kind of structure, the action becomes a distribution. So the actor network is not just output a value of action. It outputs the distribution of the action, and we select the action from this distribution. And we can see from the two equations in the bottom, and the first one, the update equation of the DQN, and you can see that DQN is a network to evaluate the Q values of every action and directly select the action with the maximum Q value. However, in arithmetic, we use a critical network. We evaluate the action A under S selected by the actor, and these two neural networks are updated together and influenced each other. So the advantage of arithmetic is a small improvement from the normal arithmetic structure. So it mainly uses a baseline to evaluate the advantage of the action under every state S. So why we need to use this baseline is because that maybe under some certain state, the actions are all good, while in other states, the actions are all bad. So directly give a value of all the actions is not stable. It's not a stable way because we cannot just tell from a value that if this action is better or worse, then the other action can be selected under this state. So accordingly, we set a baseline to tell the agent that if this action is better or worse, then other actions can be selected under this state. So the way we use the baseline, the state value Vs, it's actually the expectations of all the Q values of the actions under this state. So if we use Q minus V, it's very simple to see from it that how worse or how better is this action compared to other actions can be selected. And the change from the normal aristocratic is also simple. We just replace this cumulative reward with this advantage function. So let's go back to in our scenario. So in our scenario, there arises a new problem. We call it a synchronous Markov decision process. So we have known that if reinforcement learning is good at solving the complicated sequential problems in the random evolving environments, and the aristocratic methods can optimize both discrete and continuous variables. Like we just need to use this different action distribution in the action network. Like for the continuous action, we can use like Gaussian distribution, and for the discrete action, we can just use the categorical distribution. So it is easy. It is also easy to consider different aspects by well designing the reinforcement learning environment. So in our scenario, this is a synchronous multiple process. So the synchronous multiple process leads to two sub-problems. The first one is a synchronous MDP, and the second one is the multi-agent reinforcement learning. So for the asynchronous MDP, so what is the difference between it and the normal MDP? So in the traditional Markov decision process, when we have a state, we just fill it an action and we give it a reward as a feedback, and it will jump to the next state. And we do this round over and over again. However, in the synchronous MDP, the things are quite different, because when the agent 1, when it should select the action and we give it a reward, it will jump to another state. But this state is not the next state of this agent. This is the current state of the agent 2. So to get an example, like the device success and the power allocation in our scenario, like the agent should know how to allocate the computation resources of the selected devices by the opting agent, by the agent 1. So it is completely based on agent 1. And this is a synchronous, iterative multiple processes that are connected and influence each other. So for such a novel problem, we need also to design new algorithms for it. So the mainstream of the multi-agent reinforcement learning, they use the CTDE framework, which is centralized training and decentralized execution. I won't go into too detail, but its basic idea is to use the concatenation of all states and rewards of the different agents. So we concat all the states of different agents at the global state, and we use the sum of the rewards of all the agents to every agent. So this one is a very general solution, and it is also useful in many scenarios. But in our scenarios, the states of different agents are very different, and their optimization variables are different, and the objectives of them are also different. And the state of the agent 2 is totally based on the action of agent 1, like we described in the previous slides. So here we point out the reward. Global reward is because that some reward can only be obtained after all agents have selected their actions. So for this kind of problem, we resolve novel structure. We call it a synchronous actor and hypercritic, short for AAHC. So in AHC, we use asymmetric actors. So they take in their own current state and output the selected actions. Like the blue one, the updating actor, it will take the state of the updating stage and it will output the device selection for this updating stage. And in the downlink actor, the orange one, it will take in the downlink state and output the computation resource allocation for this stage. And for this critic, we use we call it a hybrid critic. So this critic has multiple input and output by sharing the mainstream of the layers of the neural networks. So this critic has had 3 inputs. It takes in the updating state, downlink state, and global state, respectively. And they evaluate these 3 kinds of states, also respectively. So why we do not use the traditional methods like the CBT framework, right? It's because in such a hybrid reward scenario and with multiple and synchronous multiple stages, directly giving the agent extra information from the other agent is not always advisable. Because there are redundant information from the other agent and it will even impinge on the action evaluation. And for example, if we take the energy consumption in the downlink transmission stage as an important metric, and we will set it a reward to the energy consumption. But the energy consumption is it's nothing to do with the agent 1. So if we still give the energy consumption as an information to the agent 1, it's not advisable. Because the agent 1 will say that my reward is always changing, but I can do nothing with it, and I don't know why it is changing. So it's highly unstable. So therefore, we use the global advantage as a connection between the 2 agents instead of just directly giving the extra information about the state or the reward of the other agent. So here's the 2 simple update function of these 2 actors. So the basic idea is to use the sum of their own advantage plus the global advantage to update each other. So we feed the global advantage to both of the agents as we want them to have a global view of the whole system, but we don't want them to be too much influenced by the extra information, the redundant information from the other agent. So for the hybrid critic, its update function is mainly just the sum losses. So there are 3 heads. The first head taking the updating state and the value of this state. Well, it's similar to the downlink and the global state. Note that the global state here is just the concatenation of the updating state and the downlink state. So its basic idea is to evaluate the 3 kinds of things separately, and we use the weighted sum loss to update the hybrid critic. So here is the a real implementation of the neural networks, of the 3 parts networks. So you can see that for these 2 actors, we use different action distribution in the bottom layers, and we have also conducted many experiments on it. And almost among all metrics, the AHC has the remarkable performances, and especially for the retransmission rate. Which we can see that the AHC has the lowest retransmission rate, which means that it does have a global view of the whole system, which help it to obtain this lowest transmission rate. So the next interesting topic and scenario I want to introduce is the user-centered scenario. This is quite unique in the metaverse context, which also leads to a number of problems and new solutions. So why do we focus on a user-centric in the metaverse? Because metaverse is a user-centric application by design. As such, every components of the universe should place the human user at its core. And the metaverse is a universe that every user can access freely at any time and any place. So this arises a problem that, imagine that we are in the same building, but we are maybe doing different applications, such as I'm playing a VR video game, he's having VR chat. So the required frames per second, the FPS, and the resolutions, and the other metrics are all different. So for such a user-centric scenario, we need to design a more user-specific algorithm for it. So first, there are various applications across different sectors, and there are different levels of computation and communication demands. Like for in a hospital, the remote surgeries require extremely high frame rate, alongside with the hyper-realistic and the ultra-low latency feedback. Because it is a very safety-sensitive application. Well, if it's a virtual inquiry, it's not so safe-sensitive and it has a much higher tolerance. So the variations across the XR devices hardware specifications and the user inherent characteristics also lead to the different computation power and the battery capacity. Like we know that there are already many kinds of XR devices, such as the VR glasses, AR glasses, gloves, and the wearable devices. So they have totally different computation power and computation ability, and they are also distinct user inherent characteristics, such as the user crowd degree and the resolution settings and the hypothetic information data size. So with these variations among different users, there are distinct demands among those users too. So we consider a VR scenario. Like when user A is playing a game while user B is having VR chat, the required frames per second are obviously different. Like for the game, the most comfortable FPS should be like 90 FPS, while a virtual meeting only is about 40 FPS. So how to allocate the computation resources to different users is not an easy way as before. Because the user-centric scenario addresses the user-diverse problem. So when allocating these resources to these users, we must know that these users are not equal. So it requires us to give a more user-specific to the algorithm. If we use artificial intelligence, we need to give a more user-specific structure to this AI strategy. So the following figure is an example of this kind of scenario, such as there are 3 users. The first one is playing game, and the second one is doing online shopping, and the third one is having a VR meeting. And they have different devices with different local computing powers, such as the local computing power of the user 1 can support 2K high resolution, while the third one has no sufficient computing power for high resolution. So the first one, the game shopping meeting, are the different applications in this scenario, while the others are the user inherent characteristics in this scenario. So if we divide 1 second into T frames, because the FPS is just frames per second, so how to allocate the remote computation resources in each frame is a worth studying problem in this scenario. To tackle with this problem, we'll also design a user-centric reinforcement learning structure. And there are a lot of things, but I will just introduce the inside of this structure. So the key points of this user-centric structure is about the critic. It takes in the states and output the multiple values for each user. So the critic has only one input. It's the global state, the concatenation of the states of every user. But it will output multiple values. Like that is to say that the critic not only evaluates the overall value of the whole system, it will evaluate the value for each user, and we update it with this, also with the weighted sum losses from each user. So that is also we will calculate the loss for each user, and we use the weighted sum losses for updating the credit together. So we also have conducted simulations about this scenario, and you can see from this figure that the user-specific reinforcement structure is much better than the normal one. So for this simulation, we also use the state-of-art algorithm as the backbone, which is the proximal policy optimization (PPO). And the error bands are drawn because that in such a scenario, and in many real scenarios, there are a lot of random variables, such as the data sets of each user in each transmission term, and the channel gain. They are all like random evolving environments variables. So we have set a global random seed from 0 to 20, and we have drawn the error band to better evaluate these two kinds of structures. So in the real-world scenario, we often need to extend to optimize multiple tasks. That is similar to the real-time 3D reconstruction scenario we just told in the previous slides. Because in real world, the optimization variables are always more than one. So if we extend the user-centric structure to a multiple task, right, to a multiple agent reinforcement learning, and it is also possible. It's just for the agent 1, we use the sum of the advantages calculated from the agent 1 among all users. While in agent 2, we calculated the sum advantage from the task 2 among all agents. So this advantage is calculated by the reward. So we need to decompose the reward to each user and to each stage. But for now, we don't recommend to add more than 2 agents to such a structure, because in real simulation, it's quite hard to train this neural network. So I think there are many more interesting topics in the metaverse context, because it is new and it attracts much attention in both academic and industrial areas. So that is the end of my presentation today, and thank you very much for listening.
Okay, thank you for your presentation. I got one question about the global advantage value. So you show in the figure. I'm wondering, did you use 3 critical lines to estimate the up, down, and global advantage value respectively? Or
sorry, about this?
Yes.
Okay.
I want to know how do you generate the global advantage value?
Oh, the global advantage value is also self-defined. So if after the actions of all agents, there are some things come out, like the sum rate and the wrong delay, like the delay in the uplink and downlink term. So this kind of matrix can only be obtained after all agents have selected the actions, and we give the global reward to this kind of matrix. And at this stage, we use this global reward to calculate the global advantage, and we fit the global advantage with their own advantage to update the actor, and also the critic.
Okay, so the global advantage value is estimated using another critic net, right?
Okay, so the critic has 3 inputs, and it's just sharing the mainstream of the neural network layers. So if you want, you can also use 3 separate critical networks, but the training time will be much more. And the sharing the mainstream layers I think is a widely used strategy in the AI. So basically, it's evaluating the 3 kinds of parts separately.
Okay, thank you.
Oh, thanks. How do you think about some heuristics to control the actions? Heuristics, right? So we can develop some heuristics policy to control that we don't use AI.
Don't use AI. Right?
Yes.
So your question is how to use the heuristic?
How do you think about the heuristics?
I think for many scenarios, the heuristic function has a satisfactory like performance. But if this scenario is more complicated, and such as this kind of scenarios, and in the user-centric one, we need to focus a lot of things, like the computing power of each user and the different demands for each user. So for that one, I think it's hard to come up with a very reasonable heuristic function to solve this kind of problems. And if the number of the users is big, and the computation complexity will be also very huge, because reinforcement learning has a very good like strength is that it's exploration strategy. So even if the action dimension and the state dimension is very huge, it can reach like a satisfactory performance. Yeah, like in some video games, like Atari games, the state will never come out. The same state won't come out twice, but it can also get a remarkable performance in such scenarios. Thank you.
Thanks.